Silvia. Everybody aware how the concept is? Yes? 20. Deduct 5 minutes from the display, 20 minutes each, audience and speaker.
Okay. So hello everybody, I'm Silvia Crafa. I'm assistant professor at University of Padua, so I'm from academia, and I have a very theoretical background because I'm used to work about formal methods, and so type theories, equational theories, logics to reason about concurrency, and especially concurrency in foundational calculi. But in this presentation, I won't talk about theory, absolutely no theory. The formal foundation of this work, you can find every detail in my webpage. In this presentation, I want to put formal method in action. I try to apply these methods on Scala and Akka code, and I'd like to have some feedback from real programmer to understand if this kind of approach could be actually useful in some real application, at least in some domain. Okay, so let's start with some motivation. In distributed systems, one of the key issues is the coordination of concurrent entities. There are different approaches to address this problem. One proposal is to structure the code according to a protocol-oriented programming style. What is it, this kind of programming? It entails thinking and programming in terms of communication protocols. So having protocols in mind and programming according to these protocols. But in order to have an effective programming style, you must have a language that actually supports this style. So a language requires, supporting protocol-oriented programming requires high-level abstraction to express and to declare these protocols, and then some other abstraction to check the protocol compliance. If you don't have it, you cannot really apply protocol-oriented programming.
Don't you think it's...
5 minutes. Wait for 5 minutes.
I have to wait for 5 minutes.
Oh, it's okay.
Okay.
Please.
I mean, it seems a little strong to say that you require these things when people were building message-oriented systems before, in small talk or whatever. Don't you think? I mean...
But there are very different distributed systems. So this is a very general approach. And depending on the kind of system you have, protocol-oriented programming means very different things. So if you have a message passing-based distributed system, you already know that it's something related to messages, and it is what we will see. But it is not the only kind of distributed system. So this is a more general view. Thinking and programming in terms of protocol could be useful to coordinate concurrent entities. Then depending on what kind of entities you really have in your program, then protocols are different things. And different language may support this thing in very, very different way. Indeed, what are suitable abstraction for protocol-oriented programming? There is absolutely no single solution. There could be a set of solutions, and even in general, finding suitable abstraction is a very difficult issue, because a suitable abstraction must be something easy to think about, easy to reason in terms of this abstraction, but at the same time, an abstraction is good if it is expressive and it can be implemented in a way that takes into account performance and scalability. And this is a trade-off. So there are no single solution as usual. And above all, when you add an abstraction to your language, this abstraction must also productively interoperate with other abstractions that are already contained in your language. So really, there must be many, many different solutions depending on what you're working on. And even the distributed systems can be very different in nature, as I was saying before. Just as a rough distinction is between systems that are, in a sense, data-centric, that work with some amount of shared memory. These systems better fit a centralized control of distributed entities. In that kind of systems, a top-down approach to a protocol-oriented programming could be best suited. It is easier to reason in terms of a global protocol, and then to project this coordination global protocol into local sub-protocols. And this is, for instance, the methodology proposed by multi-party session types. But there are systems, distributed systems, which have a very different nature, which are usually message passing oriented. They are communication centric, and the entity are built around strong isolation principles, and they take their decisions according to just local information. In this scenario, maybe there is a bottom-up technique to compose, a bottom-up technique to harmonically compose local protocols so should be possibly more suited to this scenario. And don't forget that real distributed systems are not clearly either data-centric or communication-centric. They are a mix of different natures. They are hybrid, even in models. So again, there is a trade-off and no single solution. Okay, this was just for the general motivation. This is an overview of what I want to show you. It is essentially a single simple example, but it is a running example that we will discuss. It is written in Scala and Akka, and I want to show that even in the actor model, the well-known type state-oriented programming, which is well-known in object-oriented languages, can be applied to actor systems. What is the idea of type state-oriented programs? A type state-oriented object is an object that has different instances in different states. So an object can change its state, and when it changes state, it offers different set of messages. An actor can also be in different states, and it can have different behaviors in each of these states. But we want that actor to handle different set of messages in those different states, and that's a key difference. We want those define actors in a stateful way, but we also want to rely on the Scala compiler, the standard Scala compiler. We don't want to add anything for the moment to this compiler, and use it to type check protocol violation. So we will do it by adding types to represent actor interfaces, and we will add typed references to actor to represent actors that are in a specific state. And to keep track of the dynamic state change of the actor, we will rely on continuation passing programming style, but not just on explicit continuation passing programming, which is the solution adopted, for instance, by the Akka-typed experimental model. We want to do it in a more implicit way. So I will propose you a monad, which greatly simplifies the definition of the user code with a continuation passing style. And we obviously want that this idea of different set of messages in different state, we want it to be robust, fully robust, even when the actor is accessed concurrently by different users. And we will do it using a mixing composition with the semantics that I call the chemical semantics, because it is inspired by the chemical abstract machines that have been proposed in foundational calculi. So this is the roadmap. And the take-home messages will be that according to my view, but I want an answer from you. The style of definition of a type state-oriented actor allows you to define the actor with a clean logic and a very natural definition. And the mixing composition allows to keep this natural definition also in the complex setting. And we have a Scala compiler, which helps us to check that only the intended messages are actually handle at the intended state. So no protocol violations in this sense. But let's see. The running example is very, very simple. I consider a one-place buffer, which is an object with a very simple protocol, but not so trivial. It has two different states. A buffer can be empty or full. When the buffer is in state empty, its interface only contains the insert method. You can only insert something in an empty buffer, and inserting something moves the buffer into state full, and vice versa. In the full state, you can only ask for removal of the content and move in the state to empty buffer. Very simple. You can express this protocol with a finite state machine. I'm not saying that I want to rely on finite state machine to express protocol, not at all. The language for defining protocol is at your choice. I just use it as a picture that is easy to which is an easy representation of the protocol. So this is the protocol, but once you define this protocol, defining a corresponding buffer actor is very, very simple. You define two different behaviors which correspond to the two possible states. So the two behaviors are empty and full, as the name of the states. And in each behavior, you handle just the intended message. So the empty behavior just handles the insert message, and the full behavior just handles the remove message. And you initialize the buffer with the empty behavior because the buffer initially is empty. So this is clearly a very natural definition. We have no defensive programming because we just handle the intended messages. The problem is how to make sure that this simple definition is robust in a concurrent setting.
Oh, question from the audience. Fine.
Yeah,
Great.
sure.
Okay, so hi. I was wondering, so if so here in this example, you have two states, and in each state you have one message. So how would the code, how would you express, let's say that in the empty state you have two messages? Because here the message or the state actually surfaces as a function definition.
Yes, the function is a partial function which can be defined in with the number of patterns you prefer. So you can define here another case with a different message you want to handle in that state.
Okay, so it would be like empty colon and then the different message? If you had another message?
You add a line here with the corresponding case.
Oh, I
Each
see.
allowed message is a case class. You have to define the case class
Okay.
in the beginning,
Okay,
and then you
I get
decide
it.
which case class to handle.
All right,
each.
thanks a lot.
Okay, it is a partial function. Okay.
Yes. How do you get the value when calling remove? Because
In this simple example, you just remove the value, you empty the buffer, you're not interested, but you can define an answer message. So entering the remove will get the value to the user with an additional message, reply message. This is a simple example when you are not interested in the value. Okay, just to keep it simple. Okay. So what are the possible errors you can make? If you have just a single user, which makes this sequence of message send, well, the first message send is bad because it sends an hello message to the buffer, which is not intended to answer hello messages. So we want the compiler to signal this message send as an error. But also here you have two remove messages in sequence, and you don't want it because asking for a removal moves the buffer into the empty state, which is not able to handle a further remove message. Okay, so you have to ensure that insert and remove are in alternation, are in sequence. Okay. So this is already a difficult problem, even if you have a single user, but the setting is more complicated when you add multiple concurrent users.
I ask you, so in previous example, how would the program, when it returns an error, in the last example, how would that know if it's a bad state or a bad message, if messages are defined only encapsulated in a state?
Well, the protocol of the buffer should, the user should be aware of the protocol, and he defines his code according to the protocol, and I want the compiler to signal that this code does not compile because it doesn't respect the assumed protocol. So the user will not compile. Okay. This is the general case when, in this example, you have two concurrent users, a producer which just makes insert requests, and a consumer which makes just remove requests. Since in this scenario there is concurrency and non-determinism, you cannot assume that insert and remove are handled in sequences. So, for instance, an insert message can arrive to the buffer when the buffer is still in the full state, so it can arrive at the wrong moment. But we want to still ensure the correctness of handling of these messages, keeping the definition of the buffer simple as up there. And this is where chemical semantic will help. But let's solve first the easy problem. So let's assume a single user, and let's try to use types to ensure that no other messages but insert and remove are admitted. The problem is that in akka, the send message tell is actually untyped because it accepts any kind of values. We want to add a layer of typing on top of this untyped sending, and we can do it by adding by wrapping the actor reference into a wrapper class, which is a typed wrapper with a generic type state encoding the state of the actor. So we let types represent actor interface. So if an actor is at state T, a typed reference at type T represents an actor with interface T at state T, and it only allows messages which belongs to the interface T, which means that you can only send arguments to the type tell methods which are of type T, so which belongs to the actor interface. And once you statically type checked your message send, you use the usual tell operation.
But that's clearly not enough if to represent the alternative state, right? I mean, with this type, I can send the insert message, but then I still have the same type. I can always send the insert message and never the remove message. So there's something missing there, right?
It is just the beginning. Yes.
Well, that's the spirit of the chess timer talk, right?
Yeah, you're right. This is an actor which is at state T, but which cannot change its state, as you're saying. So it is okay for a stateful actor, but here it is, the example, which is exactly what you mentioned. Okay, you declare a buffer, which is an empty buffer, so it allows just insert messages, which belongs to the producer interface. So you compile the insertion, but once you have inserted something, you cannot remove it because your buffer is still at the previous state. So you're not tracking the dynamic change of the states, okay? The problem is that statically, you cannot change the type of a reference. Okay, you can only assume an abstraction of all the types that reference can assume runtime. So you can resort to this continuation passing style technique, which means that instead of changing the type of the same reference, you change the reference each time. So whenever you send a message that makes the buffer change state, you change the reference according to the new type. Here it is, okay. So you have to, to introduce continuation. You can do it in an explicit way or in an implicit way. Let's start with the explicit way, which are similar, as I said, to the akka type solution. Besides the insert and remove messages, you have to add the reply messages, which reply sending to the user the continuation at the correct type. So for instance, when you ask for an insertion, you send a value, but you also send your reference because you are waiting for a reply. So the second parameter up there, okay, is a reply to. It is a reference of the user, which is expecting an insert reply message, which carries a continuation, which is a buffer ready to be consumed. Okay, so the buffer actor has the two behaviors with just the intended messages, but besides changing its state, he also reply to the user carrying self at the new. Oops, this is a consume interface. This is how the user code is changed. Here you say that you insert something into buffer, and then you wait for an insert reply, and you use the continuation O to send remove, and so on. Okay, this is a well-typed code. It ensures that there is an alternation between insert and remove, but it is not so evident that It is a sequence of insert, remove, insert, remove. The explicit continuation makes the code a little bit involved. So what I propose is to substitute them with implicit continuation and change this code into this one. In this code, you stick to just insert and remove messages, no reply messages, and the continuation are implicitly passed by means of a monad that I will explain in a moment. But just look at the user code, which is using a monad in the for notation. Actually, it is based on the future monad. So Scala programmers that are used to programming with futures should find this notation familiar, because it is like using futures. And here you see you rebind each time. You use the same variable O that is rebound in each line to use the same O, but which have different types in each line. Okay.
You have to ask more questions.
Okay, I'm cheating a bit because the code which compiles is this one. You cannot have a simple O here. You have to help the compiler with typing. So you have to use some phantom types. I don't know, entered into the details, but this is the code which actually compile. And here, if you try to make two insert, the compiler complains. Okay.
So it may be a bit early for this question, but to get into just talk. So in Akka, one of the properties of an actor ref is that transparently to the consumer, the actor can, for example, crash and reinitialize itself. But then it will reinitialize to the initial state. But if you still have a typed actor ref of the second state, that could be a problem, right?
Okay. I didn't consider fault tolerance problems at this stage, and this is indeed the major thing. It must come. But I think that it is useful here, the difference between the actor class and the actor reference class. And this is a wrapper around the reference class. So you can rebuild the actor class and take the same, and continue with the same actor reference, so with the same typed actor reference. That is the idea, but well, you have to decide what to do with the new starting with stage. Okay. My feeling is that when you come to fault tolerance problems, you have to consider those at the protocol level. So how to deal with protocol failure should be considered at the protocol level. And now I'm going to encode protocols as types. So if the protocol is fault tolerant in some sense, even the type would consider also these problems. But in general.
Cool.
I foresee a way to cheat the system here, but so I think that there is nothing that prevents me from just calling type_tel and then ignoring the continuation and just call another, make another call to type_tel with the same insert, and again ignore the continuation. So I could fold the type system in that way, or is there any protection against that?
Thank you for the question. Indeed, you can do a lot of bad things if you want. The easiest bad thing is to use the buffer reference more than once and continue to call this line. Buffer type_tel insert is well typed, and you can continue to do it. The problem is that references must be used according to an affine logic. Behind the scene, there is a linear logic, linear typing, which takes into account how many times you use a reference. The idea is that you can use this reference at most once. How to ensure this policy? Well, if you want to ensure it statically, you must add linear types to the type system. So you have to change the compiler. You can easily do it transforming this in a runtime error. If you add to typetel a flag which says whether this typetel has been called or not, so you add to the typed reference, you add a flag saying that typetel has been already called. When you try to call it the second time, it results in a throw an exception. So you moved an affine problem. You encoded the affine problem into a runtime error, but you don't like, I think, to increase the runtime errors. But this is a linear problem. Okay. I think that one. Okay, sure.
Actually, my question was almost answered, but you mentioned that you need like better type system. But I mean, Haskell can actually manage that. For example, they have state monad that actually ensures that state only used once. Is it like just scala out type system not powerful enough in this case, or?
Are you saying that Haskell already handles linear types?
Well, I mean, you can model them because, in a sense, with the type system, you can prevent reference escape. This is like, I mean, so that's why, for example, you can sort of like encode state monad. So you use only state only once, and that's it. And the type system pretty much ensure it, and without like assumption about linearity and something like.
I think that the problem might be similar to this one. If you use the monad correctly as it is, okay.
No, but I mean, Haskell ensures like statically that you only use it only once by use of type system, and it's yep. So, is it just Scala not powerful enough, or?
So there's an answer over there. Completely different scenario. The linear thing in Scala is something you cannot reference. Like you don't have access to that state. There is no state like value in the system that makes yours linear. It hides it inside the monad, and that's why it becomes linearity. The third thing, you need to be able to explicitly talk about it. And so she can't make sure they don't use the same variable multiple times.
Yeah. If you hide the reference and you let just the monad to handle the reference, you can design the monad so that it makes it correctly. But once the reference is exposed.
So what happens if you have two references to the same actor, and both references are in the empty state, and they both try to insert at the same time?
Yeah, this is indeed what I'm going to. Let's go to the answer. The example is this one. You have just a buffer which is shared by two users which want to use it in a different way, but at the same time. Each one cannot assume that the state is empty or full, because the state might be changed by the other actor. So how address this problem? In akka type, you can change the state, but in each state you must handle the same interface. Okay, so this is an easy solution, because you say that both in empty and full you can handle both insert and remove. So actually the state changes, but not the interface. What I'm doing here, the solution is resorting to the chemical idea. The chemical model of concurrency looks at the concurrent system in this way. A state is a soup of messages that have been sent to the concurrent entities. The behavior of the system is written in terms of reaction rules, and a reaction rule consumes a set of messages and produces a new set of messages. This is the chemical idea. And main point is that you keep a molecule until a reaction is triggered. And our solution is indeed keeping an incoming message until it is the correct time to handle that message. Okay? So we keep an incoming message which belongs to the protocol. So we keep a protocol message until the buffer enters the correct state to handle that message. And so these were the buffer with two behaviors. We just handle insert and remove. And to make it robust with the chemical semantics, you mix in the chemical trait. You see that the behavior still define the intended messages. What changed was this chemical react and chemical become. So the magic is there. And chemical React just stashes the incoming messages, and when enters the correct state, it unstashes the stashed messages and handles them because it is the right moment. So this is the magic.
What you just described is a recipe for disaster rename production system, because it will lead to the queue explosion, and like if you have an unbound buffer, it will explode eventually.
Okay, thanks for pointing it. Indeed, scalability problems must be taken into account. At this stage, I didn't consider them, but one idea is that what you keep and at which time keeping what, I'd like to link this to types. So at the moment, I just keep I just keep messages that are tagged with a special trait, protocol message, but I can do it more in a more fine-grained way using subtypes. So I do not want to keep all the messages, but just those that eventually will be handled. And I think that this kind of problem might be addressed using this fine-grained typing, but who knows?
A related potential problem might be deadlocks. I mean, I might be trying, I might be trading runtime errors of the kind of message not understood for deadlocks with two actors basically trying to send the remove message, and basically they're just both waiting for something. And in that case, I might prefer to actually have my runtime error saying there is something wrong here than just observing, well, not observing anything, which is what deadlocks typically do.
Okay.
You want to answer that directly?
And also on a similar topic, do you have any way to represent timeouts or like invariance for any time-related thing? Like I don't want, for instance, as a client of an actor to wait for more than n seconds.
Okay, not explicitly, not yet, but the monad I'm writing here, okay, is based on the future monad. So you have a timeout, implicit timeout when you use monad, when you use future. So, well, behind the scene. But I agree that for a robust version of this approach, you must handle also explicit timeouts.
So, similar to what he said, you kind of run back into the Erlang problem of A, you're keeping messages around in the stash, and B, every time you change state, basically you have to look through the stash like, is there something I can apply this to now, right? So you kind of have to look both through the stash and to the new messages to see, okay, which one can I take now, right? And the standard solution to this in Erlang was basically to always have an handle all case, which makes the whole thing completely pointless, right? I mean, then you basically, everything you did was like, okay, and I'm just going to sidestep it because practically it's not helpful. So.
Yeah, yes, I'm hoping, and I'm asking you if you see that instead of keeping everything, you rely on types saying what to keep. Here, the trait, you can decide when mixing this trait in or not, and what kind of which type messages you keep and which not.
Even if they're protocol messages, you might still end up the protocol just being such that the state that actually takes this message is so rare that it still ends up being there for almost forever.
Let me show this example. Okay. Okay, this is a much a bigger protocol. This is a bookshop server. You can initially add a number of books you want, and then you can check out. There are a lot of states. Each round is a state. I don't want to keep all these messages. When I decide how much interleaving I want in my program, I decide which message to take. For instance, if I decide to keep only the message that starts an interaction with a new user, I just keep the add message and I skip all the others. If I want to much more interleaving, I start to keep both add and checkout messages. So I can be really fine-grained if I decide which message marked with a trait and which not.
All right, can you go back to the slide with the two users?
Yeah.
So one thing to observe is that neither of these users will type check using the same actor type. Right, according to your system, you can only have an insert after a move, after an insert, so you wouldn't be able to write such programs.
Okay. No.
That said, so that's not that's a good thing. So these problems that we're considering aren't actually problems. What you need basically is okay, if I have an actor for this, I can create two actors from that. One of which goes to the producer and one of which goes to the consumer. And these two actors coordinate with each other. So basically, they say, okay, I've made a choice that's been inserted. Now it's your turn to make a choice that's inserted. And you can choose the synchronization policy that you want. So you could either have both sides be synchronous, right? The insert basically waits every single time, or you could have it be asynchronous and you queue up a bunch of messages using an unbounded buffer. So all these different situations are all these complaints are because different situations need different solutions, and you can make that something that people could do manually or provide convenient libraries for doing that for them rather than have a global solution that everyone has to use.
I'm not sure I understood your question, but I want to point out that a buffer that will be used just by one user as a different protocol from a buffer that it can be used by a producer and a consumer. So once you first of all, you think in terms of protocols. So if your buffer is intended to be used in this mode, it will have an according protocol. So here, in this protocol, the answer to an insert will go back to the producer as again a type which allows a second producer. Let me show the code of these two. Okay. Here you have the producer, which receives a buffer reference, which has the interface, producer interface, and it will not change its interface because its protocol is continuously inserting messages, while the consumer receives the buffer as with a consumer interface, which will never change, and the same buffer is shared, and the contravariance of the type the reference allows you to share the buffer with the correct subtypes.
Right. I see.
Okay. But this is because you started with deciding the protocol. Okay.
So back to the speaker. You need to go back to the speaker.
How many minutes?
4.
Let's go with the question.
Is that a way of having?
Okay. Is that a way to limit the rate of the request, because that is waiting to the right state? So it's like back pressure.
But it is. There are futures, so there is no blocking at all.
Mm-hmm.
So maybe I didn't understand.
I think you have answered the question.
Okay. I can use 1 minute of my time to explain why there are futures there. Okay. The idea is that beside having a typed reference around the actor reference, the new class protocol reference encodes. It's up there. It encodes the current state of the actor with the type T, but it also encodes the state transitions that are allowed for this actor by using a function, a typed expression, which is protocol, which carries the type of the continuation. So the type tel now returns a value, which is a continuation. It is an instance of the continuation class. And the continuation class contains an abstract type, which is the next state, the next interface. And it contains a pair of a promise and a future, which are linked. And the promise and future carries the typed reference at the next state. So whenever you call type tel, the user gets back the future. Okay, so it can continue with that future. You will not blocked, and the promise is forwarded to the actor. And when the actor enters the correct style, it will complete the promise, and it will unblock. It will complete the future and let advance also the user. So behind the scenes, there is this pair of promise and future.
I have a question. Like, do you hear? Essentially, you are modeling linear types in a language that doesn't support linear types.
Yeah.
Yes, but if you, for example, like would use that like in a language like Rust have like perfect. It seems like it's like perfect way to implement this because they have like move semantics, so you can just have like consumer and I mean it's just like linear type system. So what do you think about using different language for implementation?
Yeah, that's the kind of feedback I'd like to have. There are two ways. One is we have a behavioral typing, which is proof that it is sound, that it is developed on the joint calculus. Okay, we have wonderful type system, and we want to apply it. So either you find a language which is ready to apply that type system, otherwise you find a language where this typing discipline might be useful. So my idea is that actor programmer can profit from protocol-oriented programming using that kind of type. If yes, it may be worth to further explore the Scala compiler to add what it is not there. Otherwise, if you say that Rust might be a more suitable language, well, what kind of program application written in Rust?
Well, very small one, but yeah.
But
I understand. Yeah, now I see.
That's the point.
It's like your point.
1 minute, so I'll get to conclusion. It was essentially that. Okay. It was just to resume the results. So I tried to convince you that a type state-oriented actor can be an actor that can be defined with a clean logic and a literal definition, and by means of the chemical mixin, the simple definition scales to the concurrent axis. But with those problems of scalability of stash and stash message that we mentioned. And then what about protocol compliance? The idea is to express protocol with some language you prefer, and then possibly automatically convert this protocol written in this language into a type, or any kind of type expression, okay, and let the compiler do the work. And we have seen that protocol violation can be already checked by Scala compiler, which ensures that only intended messages are handled at the intended state. What is not supported at all, and again it is a problem of linear types, is compliance with protocol obligation. If the protocol is sent, you must send a remove message, first an insert, and then you must also send a remove, while these kind of obligations are not checked, because type safety is just absence of error, not wrong states, but ensuring that the correct state will be reached is not the work of the standard types. So this really requires linear typing. And so these were, but you already, do you think that this approach of type state-oriented discipline could be useful in distributed system? What kind of application? Maybe just a simple application. I'm not saying that this is the solution for everything, but the idea is to have a toolbox of programming style that can be used in different situations. And also, what kind of property would you like your compiler to check in this scenario?
Okay, thank you, Silvia. Thanks to the audience for the big interaction. Thank you very much. Welcome, Silvia. Is everybody aware how the concept is? Yes? 20. Deduct 5 minutes from the display, 20 minutes each, audience and speaker.
Okay. So hello everybody, I'm Silvia Crafa. I'm assistant professor at University of Padua. So I'm from academia, and I have a very theoretical background because I'm used to work about formal methods, and so type theories, equational theories, logics to reason about concurrency, and especially concurrency in foundational calculi. But in this presentation, I won't talk about theory, absolutely no theory. The formal foundation of this work, you can find every detail in my webpage. In this presentation, I want to put formal method in action. I try to apply these methods on Scala and Akka code, and I'd like to have some feedback from real programmer to understand if this kind of approach could be actually useful in some real application, at least in some domain. Okay, so let's start with some motivation. In distributed systems, one of the key issues is the coordination of concurrent entities. There are different approaches to address this problem. One proposal is to structure the code according to a protocol-oriented programming style. What is it, this kind of programming? It entails thinking and programming in terms of communication protocols. So having protocols in mind and programming according to these protocols. But in order to have an effective programming style, you must have a language that actually supports this style. So a language requires, supporting protocol-oriented programming requires high-level abstraction to express and to declare these protocols, and then some other abstraction to check the protocol compliance. If you don't have it, you cannot really apply protocol-oriented programming.
Don't you think it's
5 minutes? Wait for 5
I
minutes.
have to wait.
Oh, it's okay.
Okay.
Please.
I mean, it seems a little strong to say that you require these things when people were building message-oriented systems before, in small talk or whatever. Don't you think? I mean.
But there are very different distributed systems. So this is a very general approach. And depending on the kind of system you have, protocol-oriented programming means very different things. So if you have a message passing-based distributed system, you already know that is something related to messages, and it is what we will see. But it is not the only kind of distributed systems. So this is a more general view. Thinking and programming in terms of protocol could be useful to code-oriented programming, which is well known in object-oriented languages, can be applied to actor systems. What is the idea of type-state-oriented programs? A type-state-oriented object is an object that has different instances in different states. So an object can change its state, and when it changes state, it offers different set of messages. An actor can also be in different states, and it can have different behaviors in each of these states. But we want that actor to handle different set of messages in those different states, and that's a key difference. We want those define actors in a stateful way, but we also want to rely on the Scala compiler, the standard Scala compiler. We don't want to add anything for the moment to this compiler, and use it to type check protocol violation. So we will do it by adding types to represent actor interfaces, and we will add typed references to actor to represent actors that are in a specific state. And to keep track of the dynamic state change of the actor, we will rely on continuation passing programming style, but not just on explicit continuation passing programming, which is the solution adopted, for instance, by the akka-typed experimental module. We want to do it in innate concurrent entities. Then depending on what kind of entities you really have in your program, then protocols are different things. And different language may support this thing in very, very different way. Indeed, what are suitable abstraction for protocol-oriented programming? There is absolutely no single solution. There could be a set of solutions, and even in general, finding suitable abstraction is very different. It's a very difficult issue, because a suitable abstraction must be something easy to think about, easy to reason in terms of this abstraction, but at the same time, an abstraction is good if it is expressive and it can be implemented in a way that takes into account performance and scalability. And this is a trade-off, so there are no single solution as usual. And above all, when you add an abstraction to your language, this abstraction must also productively interoperate with other abstractions that are already contained in your language. So really, there must be many, many different solutions depending on what you're working on. And even the distributed systems can be very different in nature, as I was saying before. Just as a rough distinction is between systems that are, in a sense, data-centric, that work with some amount of shared memory. These systems better fit a centralized control of distributed entities. In that kind of systems, a top-down approach to protocol-oriented programming could be best suited. It is easier to reason in terms of a global protocol and then to project this coordination global protocol into local sub-protocols. And this is, for instance, the methodology proposed by multi-party session types. But there are systems, distributed systems, which have a very different nature, which are usually message passing oriented. They are communication centric, and the entity are built around strong isolation principles, and they take their decisions according to just local information. In this scenario, maybe there is a bottom-up technique to compose, a bottom-up technique to harmonically compose local protocols should be possibly more suited to this scenario. And don't forget that real distributed systems are not clearly either data-centric or communication-centric. They are a mix of different natures. They are hybrid, even in models. So again, there is a trade-off and no single solution. Okay, this was just for the general motivation. This is an overview of what I want to show you. It is essentially a single simple example, but it is a running example that we will discuss. It is written in Scala and Akka, and I want to show that even in the actor model, the well-known type state